Right there. Literally right there.
Okay, we are about to enter into some new territory in this class. And here's the way we'll get it started. Here's what we've been doing. All right, we've been doing what's called the indefinite integral. And here's the notation we've been using for it. And that's just basically telling us, go find the antiderivative of this function little f, right? And we've developed all these techniques. And our answer is what we usually wrote down as capital F of x plus some constant c, right? That's called the indefinite integral. We're going to compare that now to versus what's called the definite integral. Now the definite integral is going to use almost the same notation. We're going to have this integral sign, we're going to have little f of x dx, just like that, but we're going to add a couple of little pieces. We're going to put the bottom of this integral sign a and up here b. Now normally those are going to be just numbers, all right? Like maybe this will be 1 and that'll be 5, or this will be 0 and that'll be 10 or something like that. These numbers are known as the lower limit of integration, and the top one is called the upper limit of integration. I'll explain why they're important and what they mean in a second. But that's the main difference in the notation. That's how you can distinguish a definite integral from an indefinite. No numbers there, then you're just trying to find the antiderivative of the function, right? If there are numbers there, then your answer is no longer a family of functions. Remember how the plus c created this family of functions? Remember that? Okay. This is actually going to be a number. But sometimes you actually might get infinity, or you might get negative infinity, or you might get does not exist. Okay, but most of the time it's going to be a number. And so the question is, what does that number represent? All right? So now what we'll do, bless you, is we will take some time into developing where this notation actually came from and what that number means. All right? That's what we're going to do. Because I kind of threw this symbol at you at the very beginning, right? Said instead of me telling you to go find the antiderivative, I'm just going to write this symbol down, then you understand that to mean go find the antiderivative, right? But never really gave you like any reason why we're using that symbol. So that's what we're going to develop today. And all of this comes from, I don't want to say a simple problem. It's not a simple problem, but it's a simple idea. And you got to think back way back to the common problem of trying to figure out what the area of a circle is. You go back in the day, right? Before anyone had the formula pi r squared, right? What's the area of a circle? So for a long time, humans were okay with the idea that if you had a rectangle, length times height or length times width, however you want to call it, that the area of this is just multiply the two sides together, right? L times h, that's the area of what's inside, if it's a rectangle. But what if your shape is kind of weird, like this, right? Curved. Yeah? Or what if you have some shape that's like this? What's the area? Do we have any hope at finding the area of that, the exact area? We should, right? I mean, what do you mean use geometry?
You break it up and then you solve it like that into different parallelograms.
So you can break it up into, you're saying like some sort of polygons in there or something like that? I agree, and that's the way the Chinese first approached it, all right? What they did is they said, look, it's very difficult for us to account for this, excuse me, for this curvature on the circle. Make this a little smaller so I can bring it down here. So how about we do this? And actually, before I say it, I wanted to point out one more thing. The reason why we'd want to do this has a lot to do with well, we could get into a debate about this, but people's need to like partition land, right? It's my land, that's your land, you stay there, I stay here, right? So when we divide land up, you know, there are some places like along rivers and stuff where you have uneven, not straight lines, right? So we needed to be able to calculate areas of non-rectangular shapes. Circle being one of the most natural shapes that we don't have a simple formula for, right? And by the end of class, we will prove that the area of a circle is pi r squared. We'll prove it. But here's the way the Chinese did it. They said, all right, well, we have the area, right? Whatever it is, it's the true area. I'm going to subscript it true. That's the true area. I don't know what that is, right? So they said, here's what we can do. We can get our best ruler and our best pencil, and we can start drawing very, very precise squares and rectangles in here, right? So imagine I'm coming in here and I'm filling this thing up with rectangles and all the little gaps I'm trying to fill in with rectangles, and I'm measuring all of them, and right, and I'm creating all these areas that I can calculate, right? Yes? So let's imagine I did that. That area, let's call that the area, let's say low. Okay, I'm going to call it area low. Why do you think that I'm going to call it the area low?
Because there's some dead space.
Yeah, there's some space in here, some gaps that I couldn't account for, right? Little where the curvature, you know, wherever our rectangles did not account for. That's going to be, you know, the error that we have, right? We're not accounting for that little space. But the more rectangles I get, right, and the smaller and the better you know, the more measurements I take, the better my approximation is going to be. Agree? So this area, once I add these up, I know that that area is smaller than the true area. Yeah? Yeah? Okay? Then we come in here and we do this. We say, all right, that's kind of like a smaller area. How about if I draw just a square around this? Now that area of that square I could calculate, but that would be too much, right? Right? So then I could come in here and I could start drawing rectangles in here, right? Like this. And I could do the same thing here and here and here, right? So I take the area of the full square and I start subtracting out these little rectangles in here, right? And again, I'm going to have error. I'm going to have these little pieces in here that I didn't account for. So that area, when I do that, that's going to be bigger than the true area, right? The whole square, take away all those little rectangles, should be too much. So I have an area, I'll put here high, which is bigger than the true area. So now what I've done is I've squeezed the true area between two numbers. And the better I am at measuring, right, the more precise I am, the better my calculation is going to be. And from that, the Chinese were actually able to get 22/7 as their approximation for pi, which if you do that on your calculator, 22/7 is like 3.14 something. So it's good enough for most things, but 22/7 is not pi. So that was good, but not perfect. Understand? All right. So this whole idea of like taking this and cutting it up, or not cutting it up, doing all these rectangles and measuring all of them, this actually has a technical name. This is called the method of exhaustion. And I think it's appropriately named. Can you imagine doing that? Like your task this year is to come up with the best approximation to pi that you could possibly come up with, right? So you get some guy sitting in, or some girl sitting in some room with a big sheet of paper drawing a circle with these, you know, yardsticks, trying to get this really good approximation. That would take forever, wouldn't it? It's exhausting. So, method of exhaustion. Now, this is one approach. Another approach would be to do like polygons in here, right? We could do like sorry, that's not that great, but you get the idea, right? I could do a polygon, and I can find out areas of polygons pretty easily. And the more sides my polygon has, the better my approximation. Would you agree with that? So that's another approach, and I actually wrote up some code here to kind of give you an example. So here's a circle, right? And what I could do is I could put some triangles in here. There's one triangle.
Isn't this like also like Bayes' theorem?
Duet?
Bayes' theorem?
Theorems?
Yeah.
How do you
Once add all, like, once you put those weird shapes in there.
Not sure what you mean by that. Theorems. Okay, so there's triangles, right? Agreed? We can find the area of a triangle. We have formulas for areas of triangles, just like we have for rectangles. And do you see the yellow space? That's our error, right? We still have error this way. But the smaller I make my triangles, and the more of them I have, the better my approximation is going to be. All right? You get that idea? And what would be the best approximation? I mean, what would actually be perfect? What's that? An infinite number of triangles. Think about that. An infinite number of triangles should give me the true area, but what's also incorrect, or what's the bad part of that idea? If I had an infinite number of triangles, what's the drawback to that? Is it possible? Is it even possible to have an infinite number of triangles? Think about it this way. Let me bring the size of my triangles down a little bit. Okay, so look at these triangles here. Each one of them has some angle in here, right? And that angle should be the same for all of them, right? So if I add more triangles, what happens to that angle? It gets smaller. And if I do more and more and more and more and more, right, an infinite number, what is that angle going to? 0. Really, this thing turns into a what? At some point, if you go to infinity, it turns into what? A line. And what's the area of a line? There is no area of a line. You have to have some sort of width to it, right? You have to come out a little bit so you can have this little sliver. You understand that? So on one hand, yes, the more triangles we have, the better our approximation is. On the other hand, if we have an infinite number of them, then is it even possible to define the area of a single one of them? And it turns out that it still works. And it works because of what's referred to as the completeness axiom in our number system, that as we do this, we're going to get a sequence of numbers. Okay, so let's say I do 100 triangles, right? Say I do 100 triangles. I'm going to get some answer, some number that's going to represent the area, right? It'll be an approximation. It won't be correct. It'll be off. If I do 1,000 triangles, I'll get some other number, right? Which will be close to the true area, but not exactly. Then let's say I do 1,000,000 triangles. Then I'm going to have a number, right? And what you're creating is a sequence of numbers. And that sequence of numbers is headed somewhere. Right? It's marching towards a specific value. We call that convergence. It's converging to a number. And in our number system, all convergent sequences of numbers must converge to a single number. So like this can only go to one place. And that one place is the true area. So it's not going to like go crazy at some point and jump to somewhere else. It's got to go to one number. And so we can still take the limit, let something go to infinity and get an answer. We did that in Cal 1, right? Didn't we? We let x go to infinity and we got numerical answers. Same thing's going to happen here. We can let the number of triangles go to infinity and get an answer. Understand the basic idea? Okay. Now, what we are interested in is not a circle. We'll get to that, all right? We're going to go and start with something a little more basic. So let's say right now that I have this function. It's hard to see, but this is it right here. Almost looks kind of like a square root function, a little bit, right? And let's say I'm starting it, here's the x value 1, here's 2, here's 3, here's 4, and here's 5. All right? I'm going to approximate the area underneath this function with these 5 rectangles. Now I'm going to have a significant amount of error, right? Everything that's above this, that's error, that's error, that's error, that's error, that's error, right? But those 5 rectangles, their areas added up would give me some idea, right? Basic idea. How could I get a better approximation?
Do the midline.
I mean, in terms of rectangles, what would I need to get a better?
You need more rectangles.
I'd need more rectangles, right? But let's start with this, all right? We got to start, you've got to crawl before you walk, walk before you run. Okay, so let's see if we can't come up with the formula for that area in gray there. All right, you ready to see how this goes? Let's take a look at rectangle 1. By the way, this function right here, I'm not going to tell you what it is. I'm just going to tell you it's some function, f of x, okay? So tell me about rectangle 1.
Height is 0.9.
Let's start with width. We'll get to the height. How wide is this? Now, we all have to agree that these are 5 equal width rectangles, okay? So the total distance from here to here, right, is what? 4, right? 4?
Oh, yeah.
Right, because we're starting at 1, we're ending at 5, so the total distance from here to here is 4. Got it? That's just 5 minus 1. Now, how many rectangles do we have? 5 of them. So shouldn't each of these be a fifth of that? So do you all agree that this should be 4/5? Yeah? Total width, 4, divided equally 5 times. So each one of these is 4/5 wide. Now the height is the part that's a little tricky. The height is this point right here plugged into the function, and then we're using the height, that is the height of our rectangle. Do you see that? We're taking the right endpoint of our rectangle and we're evaluating it into the function, and however high that is, I'm drawing my rectangle over. So how high is that?
9, 10.
Yeah, what is this point right here? What is this right here? 2 is a little bit to the right of it. Well, what's this? 1, and then how far is it to here?
4/5.
So let me write it this way. I'm going to plug whatever number this is here, I'm going to plug it into the function, right? So f, and then I plug in 1 plus, how far away was that again? 4/5? 1 plus 4/5? Take 1 plus 4/5, that would be 9/5, right? Plug that into the function. Whatever that spits out, that length is your height of your rectangle. Yeah? Okay. Then what is the area of this first rectangle? This times this, right? This times this. So I would say, I'm going to write it this way. F of 1 plus, I'm leaving it as 1 plus 4/5. Yes, we could add that together. Times 4/5. And also, keep in mind, you cannot distribute this through. Right? This gets plugged into the function first, which I'm not telling you what the function is. That gives you the height of the rectangle. Multiply times the width, you've got your area. So would you all agree that's a formula for the area of the first rectangle? Okay. What about the second one? What's going to change for the second one? I'll do it right here. What's going to change?
The 1 goes to 2?
Not quite 2. Think
One goes
it's
to
f,
4/5.
and then 1 plus. So the way you can look at this second endpoint, right, is that to get there you start at 1, and then how many times do we jump? 2 times, right?